All right, guys. So I think what I've got set on the schedule should pretty much stick. Yesterday I had an issue with being able to get onto anything because my account was hacked. So that problem has been resolved. So what I wanted to do is I wanted to just basically go through the first FRQ that I gave you guys and work through that, and then if you guys have any questions, we can go over that. So is everybody good with that, or can everybody hear me also? Did I mute it? Okay. All right, so that first FRQ that we have, just so you know, because we all know at this point that the test is going to be just 2 FRQs. Since it's only going to be 2 FRQs, I really do not, if they're going to put a KSP question on there, or if they're going to put an equilibrium question on there, I really don't expect it to be set up like this. Because this one gives you a point for this, a point for this. I think that they might skip some of the other stuff and then go directly to a question where you have to do multiple parts and they can assess all those parts. All right, so the question here says, a saturated solution is prepared by adding excess PbI2 to distilled water to form 1 liter of solution at 25 degrees Celsius. The concentration of lead in the saturated solution is found to be 1.3 times 10 to the negative third moles per liter. The chemical equation was given to you, okay? So anytime that we have a solid and it dissolves into water, you're going to split it apart into its ions. So essentially what you're looking at is when it dissolves, you're going to have 1 lead ion for every 2 iodide ions. So it wants you to write the equilibrium constant expression for this equation. So when we're looking at this, we're talking about KSP. So anytime that we're talking about dissolving a solid, we're talking about KSP. If you have something with a KSP value that's very small, then that means it's not very soluble. If you have a KSP that's very large, that means you're going to have more of the ions in the solution. It dissolves more. So when you write out the expression, it's still K, it's just specifically KSP, and that's equal to the products over the reactants. So you've got lead, and then you've also got iodine. And of course, since we've got a coefficient of 2, we take it to the second power. Now, normally we would have divided by the reactants. However, this is a solid, so we don't include it. Solids don't have concentrations. So that right there is just 1 point. So now it says calculate the molar concentration of I- in the solution. Well, when you write this out, okay, we can basically just look at an ice table. So we have this. All right, so initially, well, we don't care about this because it's not in part of the KSP expression. And we should have 0 of these initially. Okay. The change, well, it should go up by some number. This should go up by twice that number. And then at equilibrium, this should be equal to x. This should be equal to 2x. Well, it tells us in the prompt that the concentration of the lead is 1.3 times 10 to the negative third. So that is going to be the concentration at equilibrium. So that's equal to 1.3 times 10 to the negative third. So this is that equilibrium. Well, this has to be twice that number, so it should be 2 times 1.3 times 10 to the negative third. Okay, and then this question right here is specifically just asking what is the concentration of I- at equilibrium. So this should be equal to 2 times that number, which is 2.6 times 10 to the negative third. moles per liter. All right, so the next question says calculate the value of the equilibrium constant. So this is one of the things I said in the previous video, is that if you're going to do this, please just make sure you write out the KSP expression. Make sure you actually write everything out, because a lot of people will forget that too. They will forget to square it. Okay, so that's important. So if we want the KSP value, we just need to plug in the values of the lead iodine and the I minus at equilibrium. So that's equal to 1.3 times 10 to the negative third. This is 2.6 times 10 to the negative third, but square it. Okay, so now once you just plug it in, you're going to get 8.8 times 10 to the negative 9. And there's no value, or there's no unit for K. All right, so are we good with those parts? Okay. All right, so the next part says a saturated solution is prepared by adding lead iodine to distilled water to form 2 liters of solution at 25 degrees Celsius. What are the molar concentrations of lead and I minus in the solution? Okay, you need to be very careful about the way it's worded here, okay, because it says what are the molar concentrations. So yes, if you have 2 liters of solution rather than 1 liter, you should have double the amount of moles in that solution. However, it's asking for the molar concentrations. So it wants to know how many moles per liter you should have of the ions in the solution. It should be exactly the same. So for lead, okay, it's still going to be 1.3 times 10 to the negative third. Okay, and then the I minus will still be the same value, because it's asking for the concentration, not the amount. If it had said how many grams were in there or how many moles were in there, then that number would be different. But because it's asking for moles per liter, it's the same thing. It doesn't matter that you have 2 liters, because the ratio of moles to liters is still going to be the same. So watch the way they word things. So if it was the amount, yeah, of course, it would be double. It'd be double the amount of grams, it'd be double the amount of moles, but the concentration will stay the same. Okay, so the next part says the solid sodium iodide is added to a saturated solution of PbI2 at 25 degrees Celsius. Assuming that the volume of the solution does not change, does the molar concentration of Pb2 plus in the solution increase, decrease, or remain the same? Justify your answer. Okay, so the question is not asking you to do any kind of calculation, although you could if you wanted to. Well, actually, you really couldn't, because they don't give you the amount of the NaI. What you have to do is you just have to think about the common ion effect. So, when you dissolve this, you get lead, and then you get 2 I minuses. Well, this, okay, has sodium ions and it has I minus ions. Okay, so it has I minus. So if you dissolve this into the solution, you have some of this present now. Well, if you have an ion present already in your solution that's in this salt, it makes this less soluble. That's the common ion effect. So you have something that's already present in that solution that makes this thing less soluble. So it's asking if this will increase, decrease, or remain the same. Well, if this is less soluble, okay, that means you're going to have less lead ions in the solution. So technically, your lead will decrease. so when you are answering the question, you have to say that lead should decrease, and you have to say something about the fact that if you have the sodium ion in there, you already have the iodide present, which makes the lead iodide less soluble, which is the common ion effect. Okay, so the value of KSP for barium chromate is 1.2 times 10 to the negative 10. When 500 milliliters of a sample of 8.2 times 10 to the negative 6 moles per liter of barium nitrate is added to 500 milliliters of 8.2 times 10 to the negative 6 moles per liter of sodium chromate, no precipitate is observed. Okay, so this question right here is similar to the third video where it's asking, will a precipitate form? So essentially what you have is you have two things that you're mixing together. So you're mixing the barium nitrate and you're mixing the sodium chromate. Okay, and then that's going to give you, it's a double replacement reaction, so the barium will mix with the chromate and the sodium mixes with the nitrate. Okay, so we know that this will be insoluble, or soluble, sorry, and this is going to be our solid. That's our precipitate. Now the thing is, anything can dissolve if you have enough water. So if you have solutions to begin with that are very dilute, you may or may not get that precipitate. It really just depends on how much you have to start off with. So it says, assuming that the volumes are additive, that was nice that they told you that, calculate the molar concentrations of barium iodine, or barium ion, and the chromate ion in 1 liter of solution. So essentially what you have to do is you just have to figure out, okay, in your 500 mils, how many moles do you have present in the barium, and how many moles do you have present of the chromate? The thing you want to be careful about is that this is a 1-to-1 ratio. So for every 1 sodium chromate that you have 1 chromate. And then for every 1 barium nitrate, you also have 1 barium. Okay, so if you were to have 2, technically anytime you dissolve just one of those, you're going to have 2 bariums, but that's not the case here. It's a 1-to-1 ratio for salt to the ion of interest. So all you're going to do is you're going to take your volume and you're going to multiply it by the concentration. We're trying to figure out how many moles are present right now. So essentially you have half of that. So you're going to have half, which will be 4.1 times 10 to the negative 6 moles. Do the same thing with your sodium chromate. So that's going to be, it's the same concentration. Okay, and then that's going to give me 4. That's going to give me 4.1 times 10 to the negative 6 moles. Now, if you want the concentration, you would just divide by the volume, the new volume. So we have 500 mils of this, we have 500 mils of this. When you put them together, your new volume is 1 liter. So your new concentration for both of them is going to be 4.1 times 10 to the negative 6 moles per liter. Okay, so use the molar concentration of barium and the chromate as determined to show why a precipitate does not form. Okay, so when we're trying to figure out if a precipitate is going to form, we have to look at Q and then compare it to the K value. So essentially, we're always trying to get back to that K value. That's the ratio of reactants to products that we're always trying to achieve. Okay, Q is at any given point during the reaction. So if Q is larger than K, it's going to shift to the left. It's going to shift to the reactant side. If Q is less than K, it's going to shift to the product side. Okay, it's going to shift to the right. So what we need to do is we need to see, okay, what is the value of Q? So Q is going to be equal to my barium and to the first multiplied by chromate to the first. Because remember, this is the thing that we're interested in. So we're trying to see, okay, to what extent is this going to happen? Where it splits apart into the ions. So we already know that my concentration of my barium, okay, is going to be equal to that because it just had you calculate that. So it's 4.1 times 10 to the negative 6. And remember, everything's to the first here because it's a 1-to-1 ratio of salt to the ion of interest. Do the same thing down here. Okay, so now we're going to calculate the value of Q. And my Q is 1.7 times 10 to the negative 11th. Okay, so my K value was given to me right here. Tells me that. So K is 1.2 times 10 to the negative 10. Okay, well this is going to be smaller than that because it's to the negative 11th. So it's going to be 1.7 times 10 to the negative 11. Since Q is less than K, the reaction shifts to the right. Well, the right would be the product side, which means that any of this that you actually form in this reaction is just going to break apart again. It's not going to make that precipitate. It's going to start dissolving because there's too much water, essentially. I think that was it for the first one. Okay, so did anybody have any questions about what I just did or about KSP? Because essentially all the videos and the KSP quiz that's going to be due Tuesday, and then sometime that week, towards the end of the week, probably Thursday evening, I'm going to open up the test, and I might have a few multiple choice questions, but most of it's going to be basically FRQ based. It's going to be some probably a short FRQ on redox and then a long FRQ on KSP. Now I'm not going to be mean because I did think about putting a redox titration with the redox stuff, but since we haven't really reviewed that stuff yet, I'm going to be nice and not add that.